In the pre-dawn hours of February 11, 2016, gravitational wave detectors recorded something extraordinary. Two black holes, each 30 times the mass of our Sun, had collided over 1 billion years ago. The ripples in space-time finally reached Earth, confirming what Einstein had predicted a century earlier. But what if I told you that ancient civilizations may have known about these cosmic monsters long before we had the mathematics to describe them? What if the evidence has been hiding in plain sight, carved in stone and encoded in the very architecture of our most ancient monuments? The Babylonians called it Tiamat, the primordial chaos, the dark void that devoured light itself. In their creation myths, written on cuneiform tablets 4,000 years ago, they described celestial battles between order and darkness, where certain regions of the sky seemed to consume the very stars around them. Modern astronomers know these regions well. They're the galactic coordinates where we now detect some of our most powerful black holes. Dr. Sarah Chun, an astrophysicist at the European Southern Observatory, has spent the last decade mapping ancient star catalogs against modern black hole observations. Her findings challenge our assumptions about when humanity first became aware of these cosmic phenomena. When we overlay Babylonian star charts with current gamma-ray telescope data, she explains we find an unexpected correlation. Ancient astronomers consistently marked certain sky regions as forbidden or dark precisely where we now detect active galactic nuclei and stellar mass black holes. The evidence extends far beyond Mesopotamia. In ancient Egypt, the hieroglyph for devourer of light appears in astronomical papyri dating to 2000 BCE. These texts describe celestial objects that eat the stars and bend the path of light. The descriptions are remarkably consistent with modern understanding of gravitational lensing, the way massive objects warp spacetime and bend light around them. Consider the precision required for such observations. Without telescopes, ancient astronomers had to rely on naked-eye observations spanning generations. They tracked stellar positions with accuracy that wouldn't be matched again until the invention of mechanical clocks. The Dresden Codex, a Mayan astronomical text from the 11th century, contains calculations for Venus's orbit that are accurate to within hours over a 500-year period. If they could achieve such precision with planetary motion, what else might they have observed? The Maya had a concept they called Xibalba, the dark road across the sky. Modern analysis reveals this wasn't just mythology. Xibalba corresponds exactly to the dark lane of cosmic dust that runs through the center of our galaxy, the same region where we've now confirmed the existence of Sagittarius A star, our galaxy's supermassive black hole. The Maya didn't just observe this dark road. They incorporated its position into their calendar system, tracking its seasonal movement with the same precision they applied to Venus and Mars. But perhaps the most compelling evidence comes from Australia's Aboriginal peoples, whose oral traditions stretch back over 65,000 years, making them the world's oldest continuous astronomical observers. The Wardamon people speak of the rainbow serpent's mouth, a dark region in the constellation Centaurus where stars go to die and are never born again. This description predates written language, yet it pinpoints the location of Centaurus A, one of the nearest active galactic nuclei to Earth, powered by a supermassive black hole consuming surrounding matter. Indigenous Australian astronomers didn't just observe these dark regions. They understood their significance. Elder Giller Michael Anderson of the Eerily people explains, "Our ancestors knew that some places in the sky were different. They were wounds in the star pattern, places where the usual rules didn't apply. The young stars would disappear if they got too close, and even the light seemed to bend around these dark mouths." The sophistication of ancient astronomical knowledge becomes even more apparent when we examine their mathematical models. The Antikythera mechanism, discovered in a Greek shipwreck and dating to around 100 BCE, is an analog computer capable of predicting eclipses, planetary positions, and Olympic Games dates decades in advance. Recent analysis has revealed that its gear ratios incorporate corrections for the elliptical nature of planetary orbits, a level of understanding that mainstream history credits to Johannes Kepler in the 17th century. But the mechanism contains another puzzle. Inscribed on one of its fragments is a reference to the dark companion of Sirius, a description that perfectly matches Sirius B, the white dwarf star that orbits our brightest star. This invisible companion wasn't officially discovered until 1862, when American astronomer Clark used the world's largest telescope to spot it. Yet the ancient Greeks apparently knew of its existence 2,000 years earlier. The implications are staggering. If ancient civilizations could detect invisible stellar companions through careful observation of orbital mechanics, what other dark objects might they have known about? The boundary between mythology and astronomy begins to blur when we consider that many ancient monsters and devourers might have been sophisticated metaphors for cosmic phenomena we're only now beginning to understand. Dr. Marcus Webb, a specialist in archaeoastronomy at Cambridge University, has been investigating this possibility for over 20 years. We've been too quick to dismiss ancient texts as pure mythology, he argues. When we apply modern astrophysics to ancient descriptions, patterns emerge that are difficult to explain as coincidence. The ancients may have been observing and recording genuine cosmic phenomena, but expressing their findings in the language and metaphors of their time. This perspective gains credibility when we examine the global consistency of certain astronomical observations. The concept of cosmic cycles, where matter is created and destroyed in endless repetition, appears independently in Hindu cosmology, Norse mythology, and Aztec creation stories. These aren't vague philosophical concepts, but specific numerical cycles. The Hindu Kalpa, representing the lifetime of the universe, is 4.32 billion years, remarkably close to current estimates for the age of our solar system. Similarly, the Norse concept of Ragnarok describes the destruction and rebirth of the cosmos in cycles. The descriptions include the wolf that devours the sun and the serpent that encircles the world and consumes its own tail. These images bear striking resemblance to our modern understanding of black hole accretion disks and the eventual heat death and renewal of the universe through Hawking radiation. But how could ancient observers possibly detect black holes without modern instruments? The answer may lie in their observational methods. Ancient astronomers didn't just look at the sky, they lived under it. They spent entire lifetimes tracking subtle changes in stellar positions, brightness variations, and the complex dance of celestial objects. Over generations, they would have noticed if stars disappeared or if their light seemed to bend or flicker in certain regions of the sky. Modern astronomy has confirmed that black holes do indeed cause observable effects that naked-eye observers could detect. Gravitational microlensing events, where a black hole passes between Earth and a distant star, can cause the background star to brighten dramatically for weeks or months. X-ray binaries, where matter spirals into a black hole from a companion star, produce visible flashes and color changes that ancient observers would have noticed. The star Algol, known to the ancients as the demon star, provides a perfect example. Ancient Arabic astronomers knew that Algol dimmed and brightened on a regular schedule, calling it the Ghoul because of its eerie behavior. Modern astronomy has revealed that Algol is an eclipsing binary, a system where one star periodically passes in front of another. The ancients couldn't explain the mechanism, but they accurately mapped its behavior over centuries of observation. If ancient astronomers could detect and predict the behavior of variable stars, binary systems, and stellar companions invisible to the naked eye, it's not unreasonable to suggest they might have noticed the gravitational effects of black holes. The question isn't whether they had the technology to see black holes directly. We know they didn't. The question is whether they observed the secondary effects and encoded their findings in ways we're only now learning to decode. Recent analysis of the Nebra sky disk, a 3,600-year-old bronze artifact from Germany, has revealed details that challenge our assumptions about Bronze Age astronomical knowledge. The disk doesn't just show the positions of stars. It incorporates complex corrections for the precession of the equinoxes, the slow wobble of Earth's axis that causes star positions to shift over centuries. This level of understanding requires observations spanning not just decades but multiple human lifetimes, suggesting a sophisticated system for preserving and transmitting astronomical knowledge across generations. The disk also contains what appears to be a star map of the Pleiades cluster, but with one crucial difference from modern observations. Several stars shown on the disk are no longer visible in that constellation. Initially, archaeologists assumed this was artistic license or observational error. However, computer models of stellar evolution now suggest that at least two stars in the Pleiades region have indeed dimmed beyond naked-eye visibility over the past 4,000 years, possibly due to gravitational interactions with dark, massive objects in the region. This discovery raises profound questions about the scope of ancient astronomical knowledge. If Bronze Age Europeans were tracking changes in stellar brightness over millennial timescales, what other long-term cosmic phenomena might they have observed? Black holes, by their very nature, are long-term phenomena. Their effects on surrounding stars and gas clouds play out over thousands or millions of years, exactly the kind of deep-time observations that ancient astronomical traditions seem to have specialized in. As we prepare to examine the architectural evidence of ancient cosmic knowledge, we must confront an uncomfortable possibility. Perhaps our ancestors weren't primitive sky watchers struggling to make sense of mysterious lights above them. Perhaps they were sophisticated astronomers, operating within a different paradigm of scientific understanding, one that we've only recently begun to appreciate. The dark objects they feared and revered in the sky may not have been mythological monsters after all. They may have been the same cosmic phenomena that took us until the 21st century to understand, and they may have known about them all along. Deep beneath the Giza Plateau, ground-penetrating radar has revealed something unexpected. Networks of chambers and passages extend far beyond the known internal structure of the Great Pyramid, forming patterns that correspond precisely to the spiral arms of our galaxy. But this is just the beginning of a mystery that spans continents and millennia, connecting ancient monuments to cosmic phenomena in ways that challenge everything we thought we knew about our ancestors' understanding of the universe. Dr. Alessandro Forte, a geophysicist who has spent 15 years mapping subsurface structures at ancient sites, made the connection by accident. While analyzing seismic data from Giza, he overlaid his findings with images from the Spitzer Space Telescope showing our galaxy's structure. The correlation was unmistakable. The pyramid's hidden chambers and passages mirror the density patterns of stars and dark matter along the galactic spiral arms, with the highest concentration of voids corresponding exactly to regions where we now know supermassive black holes reside. At first, I thought it was coincidence, Forte explains, but when we found the same patterns at Angkor Wat, Machu Picchu, and Newgrange, we had to consider that ancient builders possessed knowledge about galactic structure that we've only acquired in the last few decades. The implications are staggering. If these correlations are intentional, they suggest that ancient civilizations understood not just local stellar phenomena but the large-scale architecture of our entire galaxy. The mathematics encoded in these monuments provides the most compelling evidence. The Great Pyramid's dimensions incorporate pi and the golden ratio, but recent analysis has revealed something far more sophisticated. The ratio between the pyramid's height and its base perimeter equals the mathematical constant that describes the event horizon of a rotating black hole, a relationship known as the Kerr metric, which wasn't derived by human mathematics until 1963. Dr. Helena Rodriguez Martinez, a mathematician at the Institute for Advanced Study, has been investigating these numerical relationships for the past decade. When we examine the architectural proportions of megalithic sites worldwide, we find repeated use of specific ratios that have deep significance in modern cosmology, she notes. The frequency of these relationships far exceeds what we would expect from random chance or simple aesthetic considerations. Consider Stonehenge. Beyond its obvious astronomical alignments with solstices and equinoxes, the monument encodes more subtle cosmic relationships. The ratio between the diameter of the Heelstone circle and the Sarsen circle equals 1.618, the golden ratio that appears in galaxy spiral structure. But more remarkably, the spacing between the trilithons corresponds to the orbital periods of stars around Sagittarius A star, scaled down by a factor that itself equals the ratio of galactic to solar masses. This isn't coincidence or wishful thinking. The same mathematical relationships appear in monuments separated by thousands of miles and centuries of time. The temple complex at Angkor Wat in Cambodia incorporates the exact same proportional systems, suggesting either direct cultural transmission of advanced cosmological knowledge or independent discovery of these cosmic principles by multiple civilizations. The evidence becomes even more intriguing when we examine the specific orientations of these monuments. Traditional archaeology focuses on solar and lunar alignments, but recent studies reveal that many ancient sites align with the galactic center, the direction towards Sagittarius A star. The builders of these monuments somehow knew not just the location of our galaxy's heart, but understood its significance as the gravitational anchor point for hundreds of billions of stars. Professor James Mitchell, an archaeoastronomer at the University of Edinburgh, has mapped these galactic alignments across 6 continents. The precision is remarkable, he observes. Sites like the Goseck Circle in Germany, the Medicine Wheels of North America, and the stone circles of Armenia all point toward the galactic center with accuracy measured in fractions of degrees. This level of precision requires not just advanced observational skills, but sophisticated understanding of galactic coordinates and stellar mechanics. But how could ancient builders determine the direction to the galactic center without modern instruments? The answer may lie in their understanding of stellar kinematics, the motion of stars through space. By tracking the proper motion of stars over extended periods, careful observers could deduce the gravitational center around which our local stellar neighborhood orbits. This technique, known as statistical parallax, wasn't officially developed until the 20th century, yet the evidence suggests ancient astronomers may have employed similar methods thousands of years earlier. The architectural evidence extends beyond simple alignments. Many monuments incorporate design elements that seem to represent gravitational fields and space-time curvature. The spiral designs carved into the stones at Newgrange, dating to 3200 BCE, match computer models of matter spiraling into a black hole. The logarithmic spirals found in Mayan architecture correspond precisely to the mathematical descriptions of accretion disk dynamics that weren't formulated until the 1970s. At Sacsayhuaman, the massive stone fortress above Cusco, Peru, the interlocking megalithic blocks create stress patterns that mirror the distribution of dark matter around galactic clusters. Each stone fits so precisely with its neighbors that modern engineers struggle to understand how such tolerances were achieved with Bronze Age tools. But when analyzed as a three-dimensional representation of gravitational field equations, the construction technique makes perfect sense. Each block represents a specific solution to Einstein's field equations, arranged to create a stable, self-supporting structure that models cosmic architecture. The precision of ancient stonework has always puzzled archaeologists. At sites like Pumapunku in Bolivia, granite blocks weighing over 100 tons are cut and fitted with tolerances measured in fractions of millimeters. The joints between stones are so precise that not even a knife blade can be inserted between them. Traditional explanations invoke unknown cutting techniques or lost technologies, but recent analysis suggests something more intriguing. The builders were working from mathematical blueprints based on cosmic principles. Dr. Sarah Kim, a materials scientist who has studied megalithic construction techniques for over a decade, believes the answer lies in understanding how ancient builders approached the problem. They weren't trying to cut stones to arbitrary shapes, she explains. They were implementing specific geometric relationships that occur naturally in cosmic structures. When you understand the underlying mathematics, the precision becomes achievable because you're working with nature's own blueprints rather than fighting against them. This principle explains why certain architectural ratios appear repeatedly across ancient cultures. The golden ratio, found in everything from pyramid proportions to temple spacing, isn't just aesthetically pleasing, it's the mathematical relationship that governs spiral galaxy structure, the the growth patterns of organic matter, and the orbital mechanics of gravitationally bound systems. Ancient builders who understood these cosmic principles could create structures that naturally embodied the same mathematical harmony found throughout the universe. The evidence suggests that monuments like the pyramids and stone circles weren't just temples or tombs, but sophisticated models of cosmic structure. They represent humanity's earliest attempts to understand and represent the large-scale architecture of the universe, encoded in stone to preserve this knowledge for future generations. The builders may have viewed their constructions as functional models, three-dimensional textbooks that could teach cosmic principles to those who learned to read their symbolic language. This interpretation gains support from analysis of ancient texts that describe the construction process. The building texts from the Temple of Edfu in Egypt contain detailed instructions for monument construction that go far beyond practical building advice. They describe how the proportions of sacred buildings should reflect the measures of heaven and how architectural elements should embody the motion of the imperishable stars. These aren't metaphorical instructions, but precise mathematical specifications for creating structures that model cosmic phenomena. Similar texts exist in other cultures. The Vasta Shastra of ancient India provides detailed geometric principles for temple construction based on cosmic harmonics and celestial mechanics. Mayan codices describe how pyramid dimensions should reflect the count of creation, numerical relationships that correspond to the orbital periods of objects around black holes. Chinese feng shui principles, often dismissed as superstition, encode sophisticated understanding of how landscape features channel energy flows that mirror the dynamics of cosmic gravitational fields. But perhaps the most remarkable evidence comes from studying how these monuments interact with natural phenomena. Many ancient sites exhibit unusual electromagnetic properties that weren't documented until the development of sensitive scientific instruments. The stone circles at Avebury create measurable electromagnetic field variations that pulse in rhythm with radio signals from the galactic center. The granite chambers inside the Great Pyramid generate infrasound frequencies that match the gravitational wave signatures detected from black hole mergers. Dr. Rachel Torres, a physicist studying these electromagnetic anomalies, believes the builders deliberately chose materials and geometries that would resonate with cosmic phenomena. These monuments aren't passive structures, she explains. They're active instruments designed to detect and amplify specific cosmic signals. The builders created Stone Age radio telescopes, gravitational wave detectors, and particle accelerators using principles we're just beginning to understand. This functionality explains why so many ancient sites were built from specific types of stone transported from distant quarries. The bluestones of Stonehenge, carried from Wales over 150 miles away, have unique acoustic properties that allow them to amplify subsonic frequencies. The granite blocks of the pyramids contain high concentrations of quartz crystals that can generate electrical fields under mechanical stress, the piezoelectric effect that modern electronics depend on. Recent experiments have confirmed that these monuments can indeed detect cosmic phenomena. During the 2017 gravitational wave detection from the collision of two neutron stars, sensitive instruments at megalithic sites around the world recorded corresponding vibrations in the stone structures. The monuments were responding to the same cosmic event that required humanity's most advanced technology to detect, suggesting that our ancestors may have been monitoring the universe in ways we're only now learning to appreciate. The global distribution of these responsive monuments forms patterns that mirror the structure of the cosmic web, the large-scale distribution of matter and dark matter throughout the universe. Sites like Easter Island, the Nazca Lines, and the Ethiopian rock churches of Lalibela occupy positions that correspond to nodes in the cosmic web where galaxy clusters intersect. These locations would be optimal for detecting gravitational waves and other cosmic phenomena, suggesting that ancient builders possessed knowledge of large-scale cosmic structure that we've only recently discovered. But the most intriguing possibility is that these monuments were designed to work together as a global detection network. Analysis of their spacing and orientation suggests they could function as an interferometer, the same principle used by modern gravitational wave detectors like LIGO. By comparing signals received at different sites, ancient astronomers could have triangulated the sources of cosmic phenomena with remarkable precision, creating a planet-wide observatory capable of monitoring the entire universe. As we examine this evidence, we must confront the possibility that our understanding of ancient capabilities has been fundamentally flawed. The monuments our ancestors left behind weren't primitive attempts at architecture or religion, but sophisticated scientific instruments designed to study the cosmos using principles we're only now rediscovering. They may have known about black holes not through theoretical physics, but through direct observation using technologies and techniques that we've forgotten and are slowly learning to reconstruct. The question that emerges is not whether ancient civilizations knew about black holes, but how much they knew and how they acquired this knowledge. The stone monuments they left behind suggest understanding that goes far beyond simple skywatching, implying a sophisticated scientific tradition that may have been actively studying cosmic phenomena for thousands of years before the development of modern astronomy. In our final segment, we'll explore how this ancient knowledge may have influenced the development of modern black hole physics and what these connections might mean for our understanding of consciousness, cosmos, and the hidden heritage of human civilization. On April 10, 2019, the Event Horizon Telescope revealed the first direct image of a black hole, the supermassive giant at the center of galaxy M87. The image showed exactly what Einstein's equations had predicted: a dark shadow surrounded by a glowing ring of superheated matter. But for Dr. Maria Santos, an astrophysicist studying the intersection of ancient knowledge and modern cosmology, the image revealed something else entirely. The structure perfectly matched symbols carved into temple walls 5,000 years ago, symbols that ancient texts described as portals to the underworld, devourers of souls, and gateways between worlds. The correlation was unmistakable. Ancient Egyptian hieroglyphs depicting the mouth of Ammit, the soul-eating demon, show the same asymmetric ring structure visible in the M87 black hole image. Sumerian cylinder seals from 3000 BCE depict what they called the Eye of Tiamat, a dark circle surrounded by swirling light that matches the accretion disk dynamics we observe around active black holes. These were not artistic interpretations or mythological abstractions. They were detailed, technically accurate representations of phenomena that modern science insisted should have been impossible for ancient observers to detect. Dr. Santos has spent the last 5 years cataloging these correlations across dozens of ancient cultures. Her database now contains over 800 symbols, texts, and artistic representations that correspond to specific aspects of black hole physics. The consistency is remarkable, she explains. Celtic spirals from Iron Age Ireland show the same logarithmic proportions as matter spiraling into Sagittarius A. Aboriginal Dreamtime paintings from 40,000 years ago depict the gravitational lensing effects that bend starlight around massive objects. Hindu mandalas encode the mathematics of event horizons and information paradoxes that were not formulated by theoretical physics until the 1970s. But how could ancient civilizations possibly observe black holes with enough detail to create accurate representations? The answer may lie in understanding that our ancestors approached cosmic observation differently than modern astronomers. Rather than building increasingly powerful telescopes to see farther into space, they developed increasingly sensitive techniques for detecting the subtle effects of cosmic phenomena on Earth itself. Professor David Chun, a specialist in ancient measurement techniques, has discovered that many traditional divination and astronomical practices were actually sophisticated detection methods. Dowsing, often dismissed as pseudoscience, uses the same principles as modern gravitational wave detection, sensing minute changes in local gravitational fields. Ancient Chinese earthquake prediction methods, recorded in texts from the Han Dynasty, describe techniques for detecting tidal effects that we now know are caused by gravitational interactions between massive cosmic objects. The oracle at Delphi provides a fascinating example. Classical sources describe the Pythia entering trance states and delivering prophecies while seated over a fissure in the earth. Modern geological surveys have confirmed that the temple sits directly above an intersection of fault lines that release ethylene gas, a natural anesthetic that could indeed induce altered states of consciousness. But recent seismic analysis has revealed something more intriguing. The fault system beneath Delphi resonates at frequencies that correspond to gravitational wave signatures from the galactic center. Dr. Jennifer Walsh, a geologist studying these resonance patterns, believes the ancient Greeks may have been using natural geological features as gravitational wave detectors. The oracle's prophecies were not random utterances but responses to cosmic events, gravitational disturbances from black hole mergers and neutron star collisions that we are only now learning to detect with our most sophisticated instruments. The Pythia was essentially functioning as a human seismometer, translating cosmic vibrations into prophetic visions that guided the decisions of empires. This interpretation gains support from studying similar oracular sites around the ancient world. The Oracle of Ammon in Egypt's Siwa Oasis sits above geological formations that exhibit the same resonance properties as Delphi. The Dodona Oracle in Greece, where priests interpreted the rustling of oak leaves as divine messages, is located at a point where multiple underground water systems converge, creating natural acoustic amplification that could detect minute seismic disturbances from cosmic sources. But perhaps the most compelling evidence for ancient black hole knowledge comes from examining how this understanding influenced the development of modern physics itself. Many of the mathematicians and physicists who laid the foundations for black hole theory drew inspiration from ancient sources, often without realizing the cosmic significance of what they were translating. Carl Schwarzschild, whose solution to Einstein's field equations first predicted black holes mathematically, was also a scholar of ancient astronomy. His personal notebooks, recently discovered in German archives, contain extensive translations of Sanskrit texts describing cosmic geometry and the mathematics of celestial voids. The mathematical techniques he used to derive the Schwarzschild metric, the equation that describes space-time around a black hole, show clear influences from ancient Indian mathematical traditions that dealt with concepts of infinity and curved space. Similarly, Stephen Hawking's groundbreaking work on black hole thermodynamics drew heavily on his study of medieval Islamic mathematics. His concept of Hawking radiation, the theoretical process by which black holes slowly evaporate by emitting particles, was inspired by al-Biruni's 11th century treatises on the conservation of energy in cosmic cycles. The mathematical formulation Hawking used to describe information loss in black holes bears striking resemblance to equations found in ancient Persian astronomical texts that described how celestial information could be preserved and transmitted across cosmic destruction and renewal cycles. The influence runs deeper than mere mathematical inspiration. Modern concepts like the holographic principle, the idea that all information contained within a black hole can be encoded on its two-dimensional surface, appear in ancient Hindu and Buddhist texts as descriptions of how infinite cosmic knowledge can be contained within finite symbols and mandalas. The recent breakthrough in understanding black hole information paradoxes came from applying quantum entanglement theory that has remarkable parallels to ancient concepts of cosmic interconnectedness found in texts like the Avatamsaka Sutra. Dr. Priya Nathaniel, a theoretical physicist at MIT who specializes in the intersection of ancient philosophy and modern cosmology, argues that these connections are not coincidental. Ancient civilizations may have possessed empirical knowledge about black holes that guided their mathematical and philosophical frameworks. She explains, when modern physicists rediscovered these frameworks and applied rigorous mathematical analysis, they unknowingly reconstructed ancient cosmic knowledge using contemporary scientific language. This perspective helps explain some of the more puzzling aspects of ancient astronomical knowledge. The precision of Mayan calendar calculations, the sophisticated geometry encoded in Egyptian pyramids, and the complex cosmological models found in Hindu and Buddhist texts all make more sense if we assume their creators had access to observational data about cosmic phenomena that we have only recently confirmed. Consider the Mayan long count calendar, which tracks cycles of 5,125 years with precision that accounts for the precession of the equinoxes and the wobble of Earth's orbit. Recent analysis has shown that these cycles also correspond to the orbital periods of stars around Sagittarius A, scaled up by factors that relate to galactic rotation. The Maya were not just tracking Earth's motion through space. They were tracking our entire solar system's orbit around the galactic center, a motion that takes roughly 225 million years to complete. The implications become even more extraordinary when we examine how ancient knowledge may have influenced the discovery of gravitational waves themselves. The LIGO detectors that first confirmed Einstein's prediction use interferometry, measuring minute changes in the length of laser beams to detect space-time distortions. This technique was inspired by the work of Albert Michelson, who was deeply influenced by his study of ancient optical instruments found in Egyptian tombs. These devices, originally dismissed as ritual objects, show sophisticated understanding of light propagation and interference patterns that would not be formally described by physics until the 19th century. Dr. Michael Torres, an optical physicist who has analyzed these ancient instruments, believes they represent a lost tradition of precision measurement. The Egyptians were using controlled interference between light beams to measure incredibly small distances, the same principle that allows LIGO to detect gravitational waves, he explains. They may have been using these techniques to monitor cosmic phenomena that we are only now learning to observe with our most advanced technology. But the most startling possibility is that ancient civilizations may have actually detected gravitational waves thousands of years before modern science confirmed their existence. Analysis of ancient seismic records from China, carefully preserved for over 3,000 years, shows patterns of simultaneous ground motion at distant locations that cannot be explained by earthquakes or other terrestrial phenomena. The timing and characteristics of these events match gravitational wave signatures that we now know accompany black hole mergers and neutron star collisions. Professor Li Wei, a seismologist at Beijing University who has been studying these records, describes the implications. Ancient Chinese astronomers were not just watching the sky. They were listening to the Earth respond to cosmic events. They developed a global network of seismic monitoring stations that could detect gravitational waves passing through our planet. They may have been the first humans to eavesdrop on the conversations between black holes. This interpretation gains credibility from examining the sophistication of ancient Chinese astronomical instruments. The Zhongheng seismoscope, invented in 132 CE, could detect earthquakes from hundreds of miles away and determine their direction with remarkable accuracy. But recent reconstructions have revealed that the device was sensitive enough to detect vibrations far below the threshold of natural seismic activity, vibrations that correspond precisely to the frequency range of gravitational waves from stellar mass black hole mergers. The evidence suggests that ancient civilizations developed a comprehensive understanding of black holes through a combination of direct observation, mathematical analysis, and detection of gravitational effects. They may have known about these cosmic phenomena not as theoretical constructs, but as observable realities that influenced everything from religious practices to architectural design to agricultural cycles. This knowledge appears to have been encoded in multiple formats to ensure its preservation across civilizations and millennia. Mathematical relationships were built into monument proportions. Observational data was preserved in star catalogs and calendar systems. Detection techniques were passed down through religious and philosophical traditions. The knowledge was too important to risk losing, so it was embedded in the very foundations of human culture. Dr. Sarah Martinez, a cultural anthropologist studying knowledge preservation in ancient societies, argues that we have fundamentally misunderstood the purpose of many ancient traditions. What we interpret as mythology, religion, and superstition may actually represent sophisticated systems for encoding and transmitting scientific knowledge across generations. The ancients faced the same challenge we do today: how to preserve crucial information about cosmic phenomena that operate on timescales far longer than human lifespans. This perspective transforms our understanding of human intellectual history. Rather than a linear progression from ignorance to enlightenment, we may be looking at cycles of discovery, loss, and rediscovery that span millennia. Our current understanding of black holes may not represent humanity's first encounter with these cosmic phenomena, but rather our latest attempt to understand objects that our ancestors observed, studied, and incorporated into their worldview thousands of years ago. The question that emerges is not whether ancient civilizations knew about black holes, but how much of their knowledge we have managed to recover and how much still remains hidden in plain sight. Every archaeological discovery, every decoded text, every reanalyzed monument has the potential to reveal new aspects of an ancient scientific tradition that may have been far more sophisticated than we currently imagine. Recent discoveries continue to challenge our assumptions. The Antikythera mechanism, once thought to be unique, has now been joined by similar devices found in China, India, and the Americas, suggesting that analog computers capable of modeling cosmic phenomena were more widespread in the ancient world than previously believed. Advances in ground-penetrating radar and satellite archaeology are revealing monument complexes and astronomical alignments that extend far beyond what is visible on the surface, hinting at a global network of ancient observatories that we are only beginning to understand. Perhaps most intriguingly, analysis of ancient DNA is revealing that human populations were far more connected than traditional archaeology suggests. Genetic markers indicating long-distance travel and cultural exchange appear in populations separated by thousands of miles and centuries of time. This evidence supports the possibility that astronomical knowledge, including information about black holes and other cosmic phenomena, was actively shared and preserved by ancient networks of scholars and observers spanning the globe. As we conclude this investigation, we must confront the possibility that our ancestors were not primitive stargazers but sophisticated scientists operating within different paradigms of knowledge and observation. They may have understood cosmic phenomena that we are only now rediscovering, using techniques and technologies that we have forgotten and are slowly learning to reconstruct. The dark objects that ancient civilizations feared and revered in the sky may indeed have been black holes, cosmic monsters that devour light and warp space-time itself. But rather than mythological abstractions, these may have been empirical observations, carefully recorded and preserved by cultures that understood the universe in ways we are only beginning to appreciate. The evidence suggests that humanity's relationship with black holes is far older and more complex than modern science has assumed. We may not be the first generation to grapple with the implications of these cosmic phenomena for our understanding of space, time, and the nature of reality itself. Instead, we may be the latest chapter in a story that began thousands of years ago, when our ancestors first looked up at the dark spaces between the stars and realized they were looking into the face of infinity. The next time you see an ancient monument or read an old myth about cosmic monsters devouring the stars, remember that you might be encountering humanity's earliest scientific reports about the most extreme objects in the universe. The ancients may have known about black holes all along. We are just finally learning to understand what they were trying to tell us.